Hi, Tom Anderson, Southampton. A question really mostly to Raleigh and Blake. You described lability in terms of molecular weight. It's a good starting point. You had the terrestrial DOM being high molecular weight and relatively low lability, and the autochthonous stuff of low molecular weight and higher lability. Which is a good starting point, I think, but one of the problems with going across systems into an estuary in particular is the lability of one molecule in one place can be quite different as you move from purely freshwater system into one which has salt water in it. And the examples I give are priming, so you can have high molecular weight material which just breaks down slowly in a river or wetland and then moves into an estuary and suddenly combined with low molecular weight material produced in the estuary by phytoplankton or whatever processes are happening there, suddenly it can turn over faster. And I guess the other thing is flocculation, which you didn't really mention. I'm sure it's in there somewhere, but again, how does that relate to lability? It's all of a bit of a tough area, but do you have any comment on all of that?
You want me to say something first, Blake?
Well, I could address the flocculation question. So there is flocculation, or what's in the model called coagulation parameter, which is salinity dependent and is only applied currently to what we call the high molecular weight or the highly photoreactive compounds. So as it moves into the estuary through a salinity field, then some of it is going to flock and actually go back into the particulate fraction. In terms of the first part, the priming effects, I mean, all these effects are things that we grapple with, and how when you're working in regions where you have a really strong environmental gradient in a very short distance, how you have different factors that affect what we perceive as the lability or the reactivity of something. And we haven't quite figured out how to address some of those issues. You mentioned priming as one. Another could be, different redox environments, especially in terms of sediment, organic carbon remineralization. So I don't know, and I think that once we integrate a lot of the experimental work that Maria's group has been doing and Pat Neal at CERC, we'll be able to get a probably better handle on some of those things, at least in the Road River, and how that extends out into our hopefully eventually built out larger scale model. We'll see.
I mean, I think that's a fair answer. I mean, you're not the only one who hasn't figured out how to do all of that. I'm highlighting it as I think these are the real challenges. It's a very challenging thing to have to do to move carbon via the organic matter and model that and understand that across these different systems as opposed to just in one system. And I see that's the big challenge.
Yeah, well, I can just add that what we're trying to do is find general principles that are reasonably robust, that can guide how we set up these transformations. And they are general, and they're not going to work for everything, and they might not even work across some systems and situations, but that's the approach that we're taking.
Thank you.
Hello, yeah, Alexander Bohdansky, Old Dominion University. This is a question mainly to Julia. Are you modeling all the organic substances that come out of the sediment through resuspension? Is 100% of that organic material coming into the water in your model, or do you account for possible mechanisms of scavenging some of that DOM and bring it back into the sediment? That relates to the flocculation as well.
So I've been focusing on POM. However, I think this approach could be used to look at DOM. What we've been doing for other dissolved tracers is allowing anything that's in the pore water of the seabed to be entrained into the water column, and then it can undergo biogeochemical reactions there, though.
But there's no return from the POM that you just resuspended back into the sediment.
Oh, if it redeposits,
yeah,
it can be redeposited?
Yeah, but that is not part of your model, right now. You assume that 100% of your organic material, the POM in this case, is that you get from the sediment into the water column is then just permanently entrained in the water column.
No, it can it can resettle back to the seabed unless it's remineralized or carried out of the system.
So do you use one resuspension parameter for the whole bay, or are there different resuspension parameters depending on if it's a sandy sediment at the mouth or more silty at the top of the bay?
So the model's built so it can be flexible, but right now we're assuming it erodes when mud erodes. It's hard, it's unconstrained enough that that's our first order estimate.
Any other questions for the modelers? Erika, I have a question about your presentation on the estimate of fluxes using satellite observations. So these were based on satellite observations that were once every day, or this was one specific, how do you integrate satellite observations that are once every 2 days with tidal cycles, variations in water flow and tidal exchanges?
That's a good question. Actually, what we did was we had one good image during that period, one or two good images. So we had we got the DOC concentrations, but we integrated the water fluxes for 5 days, the tidal fluxes, and then we estimated the net fluxes by integrating over all the passes. And then we had the net flux for that particular day where we had the image. And we then multiplied the fluxes with the DOC concentrations over the whole bay, essentially. Not the whole bay, but over the passes to get the net flux over that particular time. Does that make sense? So essentially, we use one image for that particular day and the net fluxes of water volume fluxes for that particular day, and multiply the two to get the essentially to get the net flux. But we need to do that because the tidal variations are quite a lot. Actually, we have tides that are semi-diurnal on the eastern part of the bay and diurnal on the western part. So so we had to essentially sort of integrate or get all the fluxes, the water volume fluxes through these bays, and then get the net amount for the day that we have the satellite data for. So essentially, that gives us a flux for that per day, essentially for the day we had the image.
Yeah. So hopefully in the future with that.
If we get multiple, definitely. If we have more multiple images, that's going to help a lot to get better estimates of fluxes. And if you get multiple images for the day, for example, you talked about how tides can change from morning to evening. You have low tides, high tides, and definitely there are variations in DOC distributions. And if you get more images, integrate multiple satellite images, it's going to make our estimates, I think, much better. And I think the second thing is also that having multiple satellite data with multiple spatial scales. Right. So as we talked, we have Landsat data, we have wheels at 750 meters, and then you have 1 kilometer. So those type of multiple data sets is really going to help us to improve estimates, because some of the passes, for example, could be less than a kilometer, the area near the passes. So we may not have very good estimates of the DOC concentrations at these low spatial scales that we are looking for. Right. So having multiple satellites at different scales is, so that's why having Landsat, for example, and I think the new series of satellites like Landsat 8 and the European satellites, for example, if we get those together, we may get pretty good. Yes, sure.
Did you have satellite images when they opened the Barataria Bay spillway?
Actually, yes. In fact, one of those, there is a Barataria Bay spillway, the Davis Pond spillway, yes. We had these Landsat images that we were collecting, getting data, monthly data. So during one of those times, we did have, we had gone out and done some field work, and we had some of the images. So we did get those information during the spillway. And in fact, the dynamics changes completely when you open the spillway. So that's one of the complications with doing this type of work, because generally you have the upper bay and the lower bay. In the lower bay, you have influence from the river. If there is a high river discharge during the spring, you get high volume of water coming to the bay. In the fall, we don't have that much water, but when you open the spillway, you have large amount of high CDOM coming from the upper bay and influencing the CDOM. So it can get really very complicated in the bay, and I think a lot more work really needs to be done there to sort of extract different
Did
influences.
it rid a lot of carbon from the bay into the shelf?
Oh, definitely. I think one of the things that we noticed was during the storms, we do have also carbon coming from the shelf into the bay, especially during high river discharge in the spring. That's when the winds blow the plume in the anticyclonic form, and some of the water gets into the bay. But during the storms or wind events, you do have setup of the water during the cold fronts, for example, especially during fall and winter. You have this, so you have this set up and set down. So the setup brings a lot of pressure water into the bay, and set down, you pushes all the material out of the bay. So the events are very important, and I think we need to catch those events.
Okay, I think, yes, thank you for a fantastic session, like the whole session.